In this video lecture, we're going to go over the answers to the first midterm. And we'll start with question 1, which asked you to do some hexadecimal arithmetic. And specifically, it asked you to sum these two hexadecimal numbers. Now, when you do this arithmetic, it's very similar to what you would do with base 10 arithmetic. So the B6, because it has only 2 digits, is right justified. So there's 2 zeros there. And now you do your addition, except that you're doing it in base 16. So 8 plus 6 is 14. So we first do this division right here, and 8 plus 6 is 14, which if you check what it is in hexadecimal is E. There's no carry here because 14 is less than 16, so we have a carry of 0 to the next item. So the next item is 7 plus B, which is actually 7 plus 11 because B is equal to 11, and that gives us 18. Well, that's greater than 16, so if you do that mod 16, so 18 mod 16 is equal to, so we have 2 here, and we have a carry of 1. So now we have, we have a carry of 1 right here. So now we have D plus 1 is equal to E. And if you're wondering, that's because D is 13 plus 1 is 14, and 14 is E. And then we have a 1 here because 1 plus 0 is 1. There was no carry from the previous position. And the answer to our problem is 1E, 2E. Moving on to question 2, it asked why we should use reference parameters for functions. For example, if we pass a string object to a function, we want you to make sure that you declare the string object as a name. And this answer is straight from the procedures notes. If you go to the procedures notes and you go to the bottom of that page, you will find that the notes give two, first of all, they give the answer. You want the convenience of using a procedure, but you don't want to make copies because that is expensive. What that means is that you can have a very large object. For example, a vector could have a couple million entries, and if you pass it by value, it's going to require that you copy the entire object, which is several million entries. Whereas if you pass it by reference, you're only going to pass either a 4 or 8 byte pointer depending on whether you're on a 32-bit or 64-bit processor. So if you have questions about this one, I suggest you go to the procedures notes, and the notes give you 2 examples where by using reference parameters, the program runs much quicker. The notes actually give you timings to show that if it's passed, the object is passed by value, the program runs much more slowly than if the object is passed by reference. Now, there is a second reason we discussed for passing reference parameters, and that's if you want to modify the corresponding argument from the calling function. But that was not what this question asked. This question specifically asked why you should use reference parameters for objects, and the reason is because it's very expensive to pass large objects by value. You would have to copy them, and that would slow down your program. The next question is a hashing question, and we wanted to see how keys would be inserted using both linear probing and quadratic probing. And you can see the key is, our hash key is simply to take our integer key and to mod it with 11, which is the table size. So the values we're inserting are 48, 39, and 62. So 48 mod 11 is equal to 4. And we see that 4 is empty, so we can insert 48 in there. Now if we're using linear probing, our next, we're assuming linear probing, so our next key hashes to 6 because 39 mod 11 is 3 with a remainder of 6. We can see that the entry 6 is already occupied. And if you remember with linear probing, we simply do a linear search from this location until we find an empty entry or bucket, and that empty bucket is 8. So the sequence of entries that we search for 39 are 6, 7, and 8. Finally, for linear probing, we have 62 mod 11 is got a remainder of 7. So we'd like to insert 62 right there at entry 7, but again, it's occupied. With linear probing, we do a linear search starting at 7. The first empty entry we find is here at entry 9, which is where we end up inserting it. And we end up looking at entry 7, 8, and 9. Now we're going to do quadratic probing. And again, our first key is 48. Mod 11 is 4. Because the fourth entry is empty, we can simply put 48 right there. Our next key is 39, and as before, when we mod it with 11, we get a remainder of 6, and we see that entry 6 is already full. So now, with quadratic probing, we are going to be looking at 6 plus I squared mod 11. So with I equal to 1, we're looking at 6 plus 1 squared mod 11, which is equal to 7. So we look at 7 and it is already occupied. So the next one we look at is 6 plus 2 squared mod 11. And you can see that is equal to 10, and entry 10 is not occupied. So we end up putting 39 into entry 10. And the entries we probed were 6, 7, and 10. Our final entry is 62. 62 mod 11 is 7, and we see that 7 is already occupied. So again, it is 7 plus 1 squared mod 11, and that's going to be equal to 8. And because 8 is an empty entry, we end up putting 62 into entry 8. Therefore, we ended up looking at entries 7 and 8. The next question is a question regarding bit manipulation, which is from the hashing and bits lecture. So we are trying to calculate a hash key. You can see that we start with an unsigned char h that is equal to 19. And if we represent 19 as a 8-bit quantity, we're going to see that it consists of 1 16, 1 2, and a 1. So if we're going to represent that using bits, there you have a 1, a 2, no 4s, no 8s, 1 16, and then none others. So that's what it looks like as an 8-bit quantity, and I've kind of grouped it into groups of 4. Now, we're going to, our algorithm, you can see, is to left shift h by 3 bits, and then exclusive OR it with the value of name of I. So in iteration 0, what we have is we're going to first left shift h, which means that these 3 bits right here are going to get shifted out. So when we do a left shift of 3, that's going to left shift out those 3. These 4 bits shift over to our leftmost ones, and 3 new bits come in here, giving us 1 0 0. So that's the shift left by 3, and then we're ANDing with name of 0. And we can see that name of 0 is A, and A is 0 hex 61. So we're ORing that with 0x61. Well, a 1 is just 0, 0, 1, and a 6 is 0, 1, 4, 1, 2, and no 1. And we're doing an exclusive OR here. So if you remember with exclusive OR, 0 or 1 is 1, 0 or 0 is 0, 0 and 0 is 0, 1 or 0 is 1. Over here, 1 or 0 is 1, 0 or 1, 1, 0 or 1, 1, 1 or 0, 1. Okay, this gives us F, this gives us 9. So after our first iteration, we have H is equal to 0xF9. Now to start our second iteration, this is what we have for H. So this was iteration 1. Iteration 2, again, we're going to do a left shift by 3. And when we left shift by 3, we're going to lose these 3 bits right there. So they're going to go away. These 4 bits will become our leftmost, will become our leftmost 4 bits. And then we're going to have 3 zeros come in here, going along with that 1. So we have 1,000. And now we're going to be AND or exclusive ORing it with name of 1. And we can see again by looking here that that's an M now. And we gave you the hexadecimal code for M was 6D. So we're actually exclusive ORing with 6D. So D is 13, which is 1, 8, a 4, and a 1. So that gives us an 8, a 4, no 2s, and a 1. The 6, like before, is no 8s, a 4, a 2, and no 1s. And when we do a exclusive OR with that, 0 or 1 is 1, 0 or 0, 0, 0 or 1, 1. Now 1 or 1 is 0. So it's a little like arithmetic, except that there's no carry. So 0 or 0 is 0, 0 or 1, 1, 1 or 1, again that's 0 like arithmetic, but there's no carry, 1 or 0, 1. If we look at this one, we have 1, 8 and no 4s and 1, 2, so that's 8 plus 2 is 10, which is equal to A. For the second one, we have 0, 8s, we have a 4 right here, plus no 2s plus a 1 is 5, so we end up with an answer of a 5. So this is our answer for iteration 2. Moving on to question 5, we asked what is the output of the following printf statement, and we added 6 to A. What you need to do in this case is you're simply going to be adding 6 to the ASCII value of A. And there's 2 ways to do it. Either you can just kind of write down the alphabet, so A, B, C, D, E, F, G. So this is plus 1, plus 2, plus 3, plus 4, plus 5, plus 6. So that gives us a G, which is our answer. Or, and I didn't expect you to do this on the exam, you could figure out what the ASCII code for A is, add 6 to that, and you would get G. But again, I always look up the ASCII codes. I wouldn't expect you to know it. The point of this question was to show you, to reinforce the fact that you can do character arithmetic and that you can get other characters by adding integers. So in this case, by adding 6 to A, we got G. The next question was something that we covered with some of the top coder questions in the labs, and it was to see if you could separate a license plate that had this format, a state name followed by a dash followed by some number of numbers, into 2 substrings, one that you'd put in state and one that you would put into count. And for this, the solution, my preferred solution, was that you use the find command to locate the dash, and that gives you the position of the dash, the index value of the dash. Then using substring, you are able to separate the two string state and number into their respective variables. So using substring 0 to dash, we get state, and then you have to remember to go one beyond the start of the dash in order to get the count. And then you don't have to put any second argument after that, because without a second argument it simply goes to the end of the string. Some of you did put something as a second argument that was longer than the length of the string. That was fine. If you put a number, a second number right here that is longer than the length of the string, it simply goes to the end of the string. Now I also saw some solutions, or most solutions, instead of using find, used a for loop to iterate through license plate until finding a dash, and that was fine, although less efficient and not as elegant as using find. It's good to get in the habit of knowing the methods that are associated with different objects like vectors and strings and using them to good effect. Here you could have saved yourself some considerable work by using the find function. And similarly, many of you, once you found the dash, were doing concatenations, string concatenations. For example, you were saying state plus equals license plate I, which gets to the right answer, but it's inefficient because you're constantly doing a series of, in effect, pushbacks. This is the other way you could, a similar thing that we saw occasionally was state.pushback, and then license plate, which I'm going to abbreviate LP, of I. Now both of these work as far as adding characters to a variable, but they are less efficient than using substring because these pushbacks keep adding one character at a time. And first of all, if the string's long, then that's order n characters. You have n characters that you're going to have to push onto the back, and that can cause several reallocations of memory for the string, which is expensive. Whereas if you just use substring, it just does the string once, the reallocation once. It's more efficient because you're only doing one reallocation of memory for substring. Whoops. So that's for substring. But if you use either plus equal or pushback, you have multiple reallocations. So that's less efficient. So again, it's better to get in the habit of using the methods that are provided for you with objects because they are the most efficient. Okay, moving on, the next problem asked you to take these three variables, name, salary, and age. Name was to be left justified in a field of 20 characters. Salary was to be right justified in a field of 10 characters with 2 decimal digits, and age was to be right justified in a field of 4 characters. So looking at the solution over here, you can see that to left justify a string, you put a minus sign, and then 20 for the width of the field. And then you have to remember that since we're using strings, it's .c_str. Printf cannot handle a C++ style string, so you have to use an old style C string when you do that. And that was a 1-point deduction if you forgot to use .c string. For the salary, you were right justifying it in a field 10 characters wide with 2 decimal points of precision. And because values are right justified by default, there's no reason to put any kind of justification character there. And finally, age was right justified in a field 4 characters wide. So it's 4D. If you put 4I, that's also correct. D or I converts a field to an integer. Moving on, the next question asked you to take a vector and pad it on the left with a certain value. And if you remember, you did this in Lab 4 where you were doing padding with PGM files. So this was kind of a reprise of Lab 4. If you remember from Lab 4, when you did padding, what you needed to do was you first had to resize the vector. So there's 3 steps here. First, you have to resize the vector. And if the original size of the vector, which I'll call vec, was size, then you need to resize it to be size plus pad characters, where pad was the parameter that gave the number of characters you were to pad with. So that was your first step. Step 2 was you needed to make room for the padding characters, and to do that, you had to pull the characters from the right-hand side. So starting here at location 5 had to be moved. The 48 and 5 had to be moved to location 8. Now that freed up location 5 and in fact becomes a whole. Now we move location 4 over to 7, so that becomes a 43. We move location 3 to 6, it becomes a 36. We move location 2 to 5, and you see this is why it was important that we do it in this order, because we've already saved the value of 5 off to location 8. So now it's okay to overwrite location 5, so we do that by putting a 25 in there. And we now need to move 1 to 4, and again you can see we already saved location 4 to location 7, so when we move 17 in here we're not losing the previous value of location 4. And finally we move location 0, or element in location 0, to location 3, and that's a 12. So step 2 is to move or shift existing vector elements right by pad spaces, because that's how many, or pad entries, because that's how many entries we're going to use for padding. And finally in step 3 we can actually do the padding. So insert pad value into the pad entries. So in this case the pad value was 6, and we put it into the first pad entries. Hopefully you see that it would not have worked to do our insert from, or to do our shift starting at the first character, that would have given us an error. So hopefully you can see that going from the front of the vector in step 2 and trying to shift the existing elements to the right would cause us to lose some information. So let's say that we had done that. Let's say we started from the right-hand side, or from the left-hand side. You can see we would have started with entry 0, and entry 0 is 12, so we would have moved it to entry 3, thus clobbering 36. Next, we would have moved entry 1, which is 17, to entry 4, and again you can see it clobbers entry 4. Now we would move entry 2, which is 25, to entry 5, thus clobbering 25. And now when we reach entry 3, you can see what has happened. When we try to move entry 3, we end up moving 12. When we move entry 4, we move 17. And when we move entry 5, we move 25. And you can see that instead of having right-shifted our existing entries, we ended up, again, duplicating entries 0 through 2. So that's the pitfall of going from the left-hand side. You have to remember this trick that when you're trying to shift elements in a vector, you need to, if you're right-shifting, you're going to have to start from the back. If you were left-shifting, you would in fact start from the left side, but we were right-shifting here. So if we look at the code for this, you can see that here's my function signature, and very importantly, we declared the vector as a reference parameter. You lost a point for forgetting that. It's a nuisance deduction, but we want you to get in the habit of passing objects by reference. It's very important. And then our pad and our value. So the first step, well, I found the old size. I just wanted to save it. And then I resized my vector to be the old size plus pad. Then I did my right shifting, and there are multiple ways to do it, but I did it by starting at the end of the old vector, that's old size minus 1, counting down to 0, and I had to right shift by pad characters. So whatever used to be at index I had to be right shifted by pad characters, which is I plus pad. And finally, I had now emptied out the leftmost pad entries, so I could just iterate from 0 to 1 less than pad and set the vector to the appropriate pad value. The next question was one involving computing the maximum score for each student in a file. And if you have some questions about what's going on here, a place that you can go to look is the Vector of Vectors lecture from January 22nd, where we went over the pseudocode for Moonglow, and it talks in detail, that lecture, about what you need to do. I'm not going to do as much detail here, but basically your issues here are that you're reading numbers until you reach a name, and when you reach a name you want to print out the maximum value. Then you're going to again read numbers until you encounter another name. Keep doing that for the length of the file. And to do this problem, you have to realize that there are 3 cases that are important. Okay? So in my solution, well, so the 3 cases are as follows. The input is a number. Okay, that's an easy case. You just check to see if that number is greater than the current max, and if it is, you set, so input is a number. If number is, say, greater than max, then set max to number. Okay, the second case is that it failed on the number and that it's a name. So the input is a name. And in that case, we need to print the name and the max for that name. And an important thing that many of you forgot to do is you need to reset max. So a fine thing to reset it to is 0 because we guaranteed that the scores were all greater than 0. But if you didn't reset max, then you would end up potentially with someone else's max score. And then the third possibility is you've reached end of file, so there is no more input. And in this case, you want to get out and quit. And this is the issue that many of you had the most difficulty with, was handling EOF correctly. And we will see, while this may seem like a natural order to do things, 1, 2, 3, this in fact won't work if we try to do it in this order. So we're first going to look at my solution. So my solution is to enter an infinite loop. I'm fine if you used a Boolean variable for it, but I entered an infinite loop. And I read the score, assuming it was an integer. If it was, then I simply checked to see if score was greater than max, and if it was, I set max to score. Now here's the important thing. I next need to check to see if we have reached EOF. If we have reached EOF, I break out of the loop because I've reached the last person in the file. If we're not at EOF, the only remaining case is we have a name because I guaranteed you the input was correct. So we first need to clear the stream, which many of you forgot to do, but you have to clear the stream before you can read it, then read the name, print it out, and reset max. Now I said that it was many of you had struggled with the EOF. So one issue was that many of you would put if cin score like this, but then you would say else, you would say something like, you basically have the structure if number, else if cin.fail, you would process the name, else you knew it was EOF, and in fact many of you would check, you'd say if cin.eof, then you would break. Okay, but the problem with this is that if you've reached EOF, cin plus fail is true. Okay, and you will end up printing the last name twice. As an example, let's just say that our input, so we'll have while true, and we'll just have two numbers, 2, 5, and Brad. And that's my entire file. So if we did this, we see that the first time we read it, it's a number, so max gets set to 2. And the second time we read it, it's a number, and max gets set to 5. Then the third time, it's not a number, so it's cin fail, so we process the name, which is Brad, and we print out Brad and 5. Now, you can see we've reached end of file, but we're coming back to the top of the loop. We read, it's not a number, because we're at end of file, else if cin.fail. Well, it failed. This was a failure, so we process the name and we print out Brad again. We print it a second time, which is incorrect. That's why it's so important that we put this check for EOF second rather than first. Now another thing that we need to break you of is please do not use EOF in a while statement. Some of you are still doing it, and it's not correct. So a common solution that I saw was while not, and remember you have to put it in parentheses like that, while not cin.eof, you would read something into score. And then if it succeeded, so actually you'd say if cin.fail, you would do your name processing. Else, you would do your number processing. Okay, but this had the same problem that the previous solution had, which is it printed the last name twice. Again, assuming that our file was 2, 5, and Brad. What happens when you do this, execute, we come in at the beginning, it's not EOF, so we read 2 into score, and our number processing sets max equal to 2. Then we come to the top, we're still not at EOF, we read 5, and 5 is a number and max gets set to 5. We come to the top, we're not at EOF, we read it, we fail, we do our number processing, and we print out Brad and 5. We're still not at end of file. Remember, EOF is not proactive. So it does not yet know that we are at end of file. So it still is returning false for end of file. So we come in here again. We fail on this read because we're at end of file. This condition, cin.fail, is true. So we once again do our name processing and print out Brad 5, and we printed the last name twice. Now we come up and we're at end of file and we're out, but it's too late. We already printed Brad twice. So again, do not use EOF in a while statement. It's pretty much going to guarantee that you do one too many loop iterations and that you're going to get the wrong result. Okay. Moving on to question 10, we have that this was a tracing problem because we want you to learn when you have a problem with your code how to trace your code. Debugging skills are basically boiled down to being able to trace your code accurately. Now, you typically can't trace it by hand like I've done here in this program because it's going to be too long. That's why you put print statements into your code at critical points. The print statements help you trace your execution by printing out information that can help you figure out where your program is going wrong, where a logic error is. So tracing is an important skill. So in this program, we're trying to write an algorithm that's going to shift all the left or all the ones in a vector to the left-hand side and all the zeros to the right. So this vector should become one with all ones on the left. And we gave you a flawed piece of code and asked you to trace it on that particular vector. So let's put that vector's contents here. So that vector's contents were 0, 1, 1, 0, 1, 1, 0, 0. So that's 0, 1, 2, 3, 4, 5, 6, 7. So if we do our trace, we start out and we start with I is 0, J is 0. And the strategy was whenever we encounter a 0 was to search forward until we find a 1 and then swap it. So we start by looking with I and skipping forward. So on we're now at line 4, and we're going to skip forward with I until either we reach the end of the vector, which is I less than size, or until we find a entry which is a 0. So we're going to keep looking while we have ones. And you can see we immediately stop because we immediately hit an entry that's a 0. So now we're going to go to line 7 and we're going to set J to be equal to I plus 1 because we're going to search ahead and look for a 1. So I gets set to 1 here. And we immediately encounter a 1. So lines 8 and 9, we immediately encounter a 1, and therefore we exit. And we reach line 11, and J is less than size. It's 1, and size of this thing is 8. So we do a swap. So our first swap, you can see, is going to be with 0 and 1. And we end up with a 1 here and a 0 here. Now we set I equal to J, so I gets set to 1. We pick up our search from location 1, and you can see it's a 0, so we immediately stop. And then we go on to line 7 and set j equal to 2. Now lines 8 and 9 are searching forward until we find a 1, but we immediately find a 1 at location 2, so we immediately stop and exit. We come now to line 11. J is still less than the size of the vector, so we swap I and j. So we swap 1 and 2, and we get a 1 here, and this becomes a 0. We now are at line 13, so we set I equal to j, and we pick up our search from line 2. Well, you can see again we immediately stop because I is equal to, or the value at location I is a 0, and we are now at line 7. We set j equal to 3. And we search ahead using lines 8 and 9 till we come to a 1. And you can see that's going to occur when j is equal to 4. We'll find a 1. So again, we come down to line 11. J is still less than the size. So we swap entries 2 and 4. So 2 becomes a 1 and 4 becomes a 0. And now we set I equal to j at line 13, and hopefully you see this is the critical error, because if we start at I now at j's location 4, instead of picking up our search at location 3 like we should have, which was 1 past the current value of I, we instead leapfrogged ahead in the vector to where the last 1 was, and we skipped over some zeros. So we actually now picked up our search at location 4, and as you can see, there is a immediate 0 there. So we stop the search for I, and we're again at line 7. We set j to be I plus 1, and it immediately stops in its search for a 1 because we find it. So we swap locations 4 and 5, ending up with a 1 here and a 0 here. And because we still haven't reached the end, we set I equal to j, which is 5. And now we again immediately stop on line 4 because I points to a 0 entry. We go to line 7 and set j to be 6 and scan forward looking for a 1, but you see this time we don't find it, which is why it's so important to have this j less than size here, because that stops us when we're no longer able to find a 1 in the vector. So eventually j gets up to be 8, and we end up stopping. We reach line 11. And see, line 11 now stops us from doing a swap because we know we haven't found a 1. And we set I equal to j, which is really doesn't matter because when we come to the top of the loop, line 3, we find that j is no longer less than size and we exit. So you can see this is our final outcome right here, 1, 1, 1, 0, 1, 0, 0. And you can see that we skipped, or we didn't get all of our 1s over to the left-hand side. Well, hopefully as you did it, you saw that the problem was at line 13 and that we were accidentally setting I to be the last location of a 1 rather than having I start its search from the last 0 that was found. So for example, when I was back here at 2 and we did our swap with 2 and 4, we needed to pick up our search with 3. So it's a very simple fix. We change line 13, and it needs to be I++. We just increment I to be 1 greater than its previous value. So if we look at the solution, you can see that's all it is. The problem is line 13. It should be I++. The final question was that we said this was kind of an inefficient algorithm because what we were in effect doing was moving each I in the vector, even if we get the vector right, okay, or the algorithm right. Okay, so let's say that the algorithm was, again, 0, 1, 1, 0, 1, 1, 0, 0. You notice that this one had to move, this one moved, this one had to move, and this one had to move, which is really unnecessary because all 4 ones ended up moving. But if you look at it, again, the original one, you can see that these 2 ones right here really don't need to move. So it was inefficient to move those ones. They should have stayed where they were. Well, remember our trick was sometimes it works to go from the back of an array or from the back of a vector, and that would work here. If we start from the back of the vector looking for a 1, we would sweep left until we came to this one right here. And now we would swap this 0 with this 1. So if we number our entries, you can see we would end up swapping 0 and 5. So we swap this 1 becomes a 0 and this becomes a 1 here. And now you can see we'd move I all the way forward, skipping over entries 1 and 2 and leaving those 1s in place and coming to entry 3. And then moving J to the left, we come to entry 4 and find that we should swap entries 3 and 4, which gives us a 1 and a 0. So we only swap 2 1s rather than 4. And in fact, you can kind of show, if you think about it, that instead of moving n 1s, on average you only would move n divided by 2, because you would expect that roughly half the 1s might already be in the right place. Now there was another approach, also equally good, which is you could go through and you could count up the number of 1s. You can see there are 4 1s here. So in that case, you know that any one that is in locations 0, 1, 2, or 3 is already in the right place, and only ones that are in location 4 and higher are going to have to move. So the other equally good approach was to start your search J at the number of 1s. Okay, remember, since we use zero-based indexing, we don't have to subtract 1. It's actually whatever the number of 1s is. So here we'd start our search at J equals 4. If we do that, then you can see starting J here at 4, we're going to swap first 0 and 4. So this becomes a 1, this becomes a 0. And then when we get I to here, J is going to move out to 5, and we'll end up swapping 3 and 5. So either approach worked. Either approach would reduce the number of 1s that had to be moved to only those 1s that weren't already in the right position. That concludes our discussion of this exam.